Hi, so welcome to the chapter 3 of S2, which is on linear combinations of random variables. So this is a particularly short chapter, so what I would do is to basically divide this particular chapter into two parts. So the first part will be more on the theory, like how to derive all the formulas. The second part will be just on the exercises. So, let's begin. So, first of all, let's recall the definition of the expected value and the variance. So, basically, what we want to study is how these two quantities varies under linear combinations of random variables, basically. So, I will quote the discrete version and then also the continuous version. So for discrete version, usually Ex is defined to be the sum of. So over here, I would use X for the index I. Later on, you see Y. So this will be XI and we do have other names. So this is mu. So I will label this as mu X. So this is the first equation. So this is a discrete version. So now the variance will be the sum of I xi square pi minus mu x square. So this will be the sort of like definitions for ex and variance of x for discrete random variables. So how about the continuous version? So remember, this is for discrete or probability distribution. So now let's look at the continuous one. For continuous one, Ex will be integrating xi pi. Sorry, in this case, it is not pi. This is a function of dx. So let's say this is the third equation. The variance of x will be, perhaps I should separate it a little bit so that you don't get too crowded and confused. So this will be the integration of xi square px dx minus mu x square. Okay, so this is equation 4. So let's also denote this as mu x. So this is for continuous probability distribution. So basically in this chapter we want to derive certain identities. So the first one, okay, the first case 1. So let's say you have y equals to some constant a multiply with your random variable x plus b. So what would be your ey in terms of ex? So I will derive the discrete one and then the continuous one. So ey will be equals to e a x plus b. So a and b are constant. So by definition, this is sum of, let's say, j, yj, pj. So I will denote all the y relevant stuff as the index j. And then you can basically change it to this. Sorry, this will be j. So a x j, because I started with j, so I have to use j over here, plus b p j. Then you expand it. So the thing is, when you have a constant multiply the variable xi or xj in this case, this will be just the same as you move the a outside and then you sum xj pj, and then you have plus p sum of j pj. So by now you should know that the sum of all j of pj equals to 1. So this means that you have a, so the sum of j xj pj, this is the expected value of x. So this will be b. Okay? So that's why ey equals to a multiplied with ex plus b when x equals to ax plus b, for example. So now let's look at the variance of y. This will be the variance of ax plus b. Then you use the definition. Definition will be sum of all j pj. So this time this will be a xj plus b, the whole thing square, and then you have minus mu x. Sorry, so originally this is minus mu y square, and because we already derived what is mu y when you have the transformation ax plus b, so this we can write it as a mu x plus b, the whole thing square. So now you break out the square terms. So you have a square xj square plus 2ab xj plus b square minus a square mu x square minus 2ab mu x minus b square. So now you multiply everything, and then the summation sign can be separated through the plus sign. So in the end you will have a square. So constant, I move it out, pj xj square plus 2ab pj xj plus b square pj minus a square mu x square minus 2ab mu x minus b square. So this is basically the same as b square, because the sum of all pj is equals to 1. So that's why, let me use a different color to cancel it off, the red color for example. That's why these two terms can be cancelled off. They are the same thing. So the other term that can be cancelled off is this 2ab sum of j pj xj, because the sum of j pj xj is basically mu x. So this term is 2ab mu x, so this can be cancelled off. So what you are left with is a square sum of j p j x j square minus mu x square. So this will be a square, the variance of x. So in conclusion, by right, when you see this kind of combination, the first thing that you need to know is, EY will be equals to AEX plus B. Variance of y will be a square of variance of x. So now let's show this for the continuous version. For the continuous version, EX is the integration of, EY is basically this. So this is integrating y, which is ax plus b, and then py. So this is dy. So notice that you need to change this to dx. This is basically integration by substitution. So if y equals to ax plus b, so then dy will be equals to a dx. So this whole thing becomes, let me break this down. So the a I factor outside. So I have x p ax plus b. So this will be a dx, and then plus b integrating p ax plus b a dx. So you might think that you don't know how to integrate this, but basically this is the same as, for example, if you have okay, so let's say you have y equals to a random function e to the power of ax plus b. So when you differentiate this, you would get ax plus b. Okay, so now you are just reversing the process, and take note that this particular whole thing is just integrating as normal. So meaning that this whole integration is just your definition of ex. That's why you have aex plus b. So this will be the same as integrating px dx. Okay, let me write down what it is, because you undergo some transformation. So this whole thing is equals to integrating x px dx. It's just that because of the integration by substitution, you have this form. So this is also because of the integration by substitution. That's why you transform into the upper form. But what really is just integrating px dx. So then you have aex plus b. So now let's look at the variance. Is more or less the same thing. Variance of y would be equals to the variance of ax plus b. So this is integrating yp, should be y square py dy minus mu y square. So you substitute ax plus b accordingly. So you have a square x square plus 2abx plus b square pax plus b. We already know from up there that dy is a dx, and then we also know that mu y is a mu x plus b, the whole thing square. So then what you have is a square x square pax plus b a dx plus 2ab integrating x pax plus b a dx plus b square integrating pax plus b a dx. So now you expand the right part, you would get a square mu x square minus 2ab mu x minus b squared. So again, let's look at which can be cancelled off. So this part basically means that once you're integrating it, you get b squared. So this is cancelled off with this. And then the other one will be this 2ab x pax plus b a dx. After the integration, you get 2ab mu x. So what you would get in the end will be a square integrating x square pax plus b a dx minus mu x square. So this will be a square variance of x. So that's how you prove the same equation over here for discrete random variable and continuous random variable. Okay, so that is the first case. So now let's look at the second one. So as I said before, we will look into the exercises tomorrow. So the second one would be a linear combination of two so this is what we call as the linear combination of two. Basically you can expand it to more, but what we are doing here is two independent random variables. So the word independent is very important. So I will state the result first. So the result would be when it is e ax plus by, this is equals to aex plus bey. If it is the variance of ax plus by, this will be a square variance of x plus b square variance of y. So now I'm going to show you how to derive this using discrete random variables and continuous random variable. Basically, they give you the same results. Okay. So let's look at the discrete version first. So from equation 1, we already know that EAX plus BY is equals to a double summation. So this time you sum I and J together. So for X, I use I. And then for Y, I use J. So now this is the part that we need to be careful. The reason why I stress this particular word independent is because for independent probability distribution, we know that Pxy is equals to Px multiplied with Py. Or rather, I can write this Px intercepting y. So two events happening together is given by Px multiplied with Py. So this is a definition of independent probability distribution. So over here, Pij is basically Px intercept with y. So then, because we already assume that those are independent, so you can break it down further. So this is basically Pi Pj. So here, take note that Pi equals to Px, Pj equals to Py. And Pij is Px intercept y. Okay. So then the next thing, you just break them up. So you have, sorry, yj, not xj, pi, pj. Okay. So now notice the indices. So for indices I, you have a xi, pi. Basically a is a constant. I can move it out. So it will be xi, pi. And then for the j one, you only have pj. Similarly over here, b I can factor it out. So I only have pi. For j, I have yj, pj. So the summation of all pj gives me 1. And the summation of I, xi, pi gives me ex. The second one, you will have b, and then the sum of all pi will be 1. So you have sum of j, yj, pj, that will give me ey. That's how you prove the first equation over here. So for the variance of ax plus by, the same thing, you go through all the definition, ij, a x I b y, sorry, what am I writing? Axi plus byj, this whole thing square and then multiply with pij, which is pi multiplied with pj. So over here we already derived from above that this is equals to a mu x plus b mu y, the whole thing square. So then you expand the whole thing. This will be a square xi square pi pj plus 2ab xi yj pi pj plus b square yj square yj square pi pj. minus expand the whole thing, you get a square mu x square minus 2ab mu x mu y minus b square mu y square. So now the next thing that you need to do is to separate out the summation. So you have a square, sum of I, you have xi square pi, and then you have sum of j pj. Then the next one will be 2ab. Okay, I should add the bracket. So now you have 2ab sum of I xi pi sum of j yj pj plus b square sum of I pi sum of j yj square pj. Then you minus a square mu x square minus 2ab mu x mu y minus b square mu y square. So now write down everything. So the sum of j pj becomes 1, so you have a square sum of I xi square pi plus 2ab. So sum of I xi pi is mu x, the other one will be mu y. Then you have plus b square. Sum of all pi will be 1, so you have sum of j yj square pj minus a square mu x square minus 2ab mu x mu y minus b square mu y square. So there's only one term that you can cancel off, it's a 2ab one. So in the end, what you have is a square sum of I xi square pi minus mu x square plus b square sum of j yj square pj minus mu y square. So this will be a square variance of x plus b square variance of y, which is given by the second formula over here. So now I'm also going to show you how to derive this using continuous random variable. So for ex, what is the definition for that? So sorry, not ex, but eax plus by. So this is the integration of ax plus by. And then you have p xy dx dy. So if it is independent random variables, pxy equals to px multiplied with py. This is by definition again. So therefore, this whole thing becomes px py dy dx dy. Then you just expand, so you have ax px py dx dy plus integrating by px py dx dy. So you can factor out the a, and then for each of the integration, you integrate according to the variables. So for example, x px dx, and then integrating py dy. So you just group them accordingly. Similarly, over here, you can move your x and y accordingly. Px dx, integrating y py dy. So integrating all of py gives you 1. So in the end, what you have is a. So the first term here is the definition of ex plus b. So integrating of all px is 1. So the second integration will give you ey, which is the same as the above. So now let's work on the variance. This is ax plus by. So the definition of variance, if you quote it accordingly, this will be integrating ax, plus by, the whole thing square. So here I directly quote the definition of independent random variables, px multiplied with py dx dy minus the mean, which we already know is a mu x plus b mu y. So this is again from the definition, from the proof that we have done above. So now you just expand everything. So you have a square x square plus 2abxy plus b square y square. This whole thing you need to multiply with px, py, dx, dy. Minus, expand the whole thing, you get a square, mu x square. Minus 2ab mu x mu y. Minus b square mu y square. So now, again, repeat the same step. You have a square. X square px py dx dy. So that is the first term. Second term will be 2ab outside. Xy px py dx dy. And then the third term will be b square y square px py dx dy. So minus a square mu x square minus 2ab mu x mu y minus b square mu y square. So then the next step is to simplify it. You have a square x square px dx, integrating py dy plus 2ab, so x px dx, and then you have y py dy plus b square. So here you have px dx and then y square py dy minus a square mu x square minus 2ab mu x mu y minus b square mu y square. So the first one will give you a square integrating x square px dx. So the last integration gives you 1. Then you have 2ab, integrating the first one will give you mu x, integrating the second one will give you mu y, plus b square. The first integration gives you 1, the second one keeps it. Then you have minus a square mu x square minus 2ab mu x mu y minus b square mu y square. So there's only one term that you can cancel off, which is a 2ab term. So once you did that, you can factorize out into a square, integrating x squared px dx minus mu x squared plus b squared integrating y squared py dy and then minus mu y squared. So this will be a square variance of x plus b square variance of y, which is again the same as this formula. So these four equations circle, not circle, within the red rectangular, those are the most general formulas. Of course, you can substitute, for example, a equals to 1, b equals to 0, and then find out what happens. But basically, those are the equations. That is the most general one. You can use it for all scenarios. And over here, I basically show you that how you can derive the same formula for discrete and continuous random variables. So tomorrow we will look at examples, and especially for Poisson distribution, you have a very limiting condition, which is the expected value and the variance, they should be the same. So not necessarily ax plus by gives you back the Poisson distribution. So that's all for today's video. Thank you.